In the previous session, we looked at the general linear group of 2 by 2 matrices which are invertible over Z2. Now let's look at its correspondence between this group and the characteristic polynomials. So each element of GL2 Z2 corresponds to a polynomial in Z2 of X via characteristic polynomials. These polynomials reveal whether the matrix has eigenvalues in Z2. Alternatively, we can see GL2 Z2 as permuting polynomials in two variable over 0, 1. So what this means, let's try to understand this. Now, in the previous session, we have already seen what are the various invertible matrices over 0, 1. So A1 is equal to 1, 0, 0, 1. Now, the characteristic matrix is xi minus A1. So xi is what? A scalar multiple of the identity matrix. Identity matrix is 1, 0, 0, 1. So if we multiply x with this identity matrix, we get x00x minus A1. Now here A1 is the identity matrix, but to keep it general, we take it as I separately. Now let's subtract these two. We get x minus 1, 0 minus 0, 0 minus 0, x minus 1. So now remember we are in Z2 or rather over Z2. So which means minus 1 is equivalent to 1 mod 2. So we can write it as x plus 1, 0, 0, x plus 1 in mod 2. Now the characteristic polynomial with respect to A1 is the determinant of the characteristic matrix. Now we know how to take the determinant, cross multiply and take the difference in case of 2 by 2 matrices. So x plus 1 times x plus 1 minus 0 times 0, which gives us x plus 1 square. Now let's find the roots by equating it to 0. So P A1x is equal to x plus 1 square. So we equate it to 0 mod 2. That means x plus 1 equal to 0 mod 2, x equal to minus 1 mod 2. And since minus 1 is equivalent to 1 mod 2, we can say x equal to 1. So therefore, 1 is the eigenvalue and multiplicity is 2 because of this square. Okay, now let's look at A2. A2 is 0, 1, 1, 0. And the characteristic matrix will work out to x1, 1x. Now we take the determinant. X square minus 1. Now x square minus 1 is equivalent to x square plus 1 mod 2 because minus 1 is equivalent to 1 mod 2. So x plus 1 square is equal to x square plus 2x plus 1 in mod 2. Now 2x, the result of this will always be an even number. That means when we take mod 2, remainder will 0. That means 2x disappears to leave x square plus 1. That means x square plus 1 is equivalent to x plus 1 square mod 2. Or we can say x plus 1 square is equivalent to x square plus 1 mod 2. Which implies the characteristic polynomial of A2 and A1 are equivalent. Because here also if you notice, we have x plus 1 square. And here also we have x plus 1 the whole square. So which means the eigenvalue will also be the same. So 1 is the eigenvalue and multiplicity is 2. Similarly, the characteristic polynomial of A3 and A4 is x plus 1 square. And the eigenvalue is 1 with multiplicity 2. A5 A5 is 0, 1, 1, 1. Xi minus A5 is equal to X0, 0, X minus 0, 1, 1, 1, which works out to X minus 1, minus 1, X. And since minus 1 is equivalent to 1 mod 2, we can write it as X1, 1, X plus 1 mod 2. So the characteristic polynomial would be the determinant of this characteristic matrix. And the determinant will be X times X plus 1 minus 1 times 1. That is X times X plus 1 minus 1, which is equal to X square plus X minus 1, but minus 1 is equivalent to 1, so we write it as plus 1 mod 2. What are the roots of PA5? Remember, we are working only with 0 and 1. So one of them has to be a root. So which means to verify it, we can directly do substitution. So let X equal to 0. What do we get? 0 square plus 0 plus 1, which is equal to 1. But what are we supposed to get? We are supposed to get equal to 0. So since it is not equal to 0, that means it can't be the root. Now if we take X equal to 1, we get 1 square plus 1, which is equal to 3, which is equivalent to 1 mod 2, again which is not equal to 0. So that means X square plus X plus 1 has no roots in Z2, which means A5 has no eigenvalues in Z2. And same thing if you do with A6, you will end up with no eigenvalues in Z2 as well. So what have we achieved? We have 4 matrices having eigenvalue 1 with multiplicity 2. That is A1, which is I itself, is 1, and the other 3 are A2, A3, A4. 2 matrices A5 and A6 have no eigenvalues in Z2 because X square plus X plus 1 is irreducible in mod 2. So we have one element of order 1 in GL2 Z2, that is the identity. 3 elements of order 2, that is A2, A3, A4. Since A2 square is equal to A3 square is equal to A4 square is equal to I. And we have 2 elements of order 3, that is A5 and A6. Since A5 to cube is equal to A6 cube is equal to I. So we have looked at the correspondence between the general linear group of invertible 2 by 2 matrices over Z2 and the characteristic polynomials. So again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.